I am a robot.
Measuring signals is an important part of being able to develop embedded systems. As you have had no experience with doing this in your previous courses, this video is going to give you an introductory tutorial on how to do this with your Beaglebone. So when you are done with this video, what you should be able to do is connect an oscilloscope to your Beaglebone to measure digital signals. In our particular case, what we're going to be doing is looking at the time difference between when a light is turned on and when a light is turned off. We're going to measure frequency, and we're going to measure essentially the amount of time that it takes, the latency between when a button is pressed and when an LED changes. So I'm going to show you those two measurements. Thus, you'll be able to use the Digilent Analog Discovery to measure time differences between signals. Now, what we're going to be using for all of our measurements is a system called the Analog Discovery. The Analog Discovery, manufactured by a company called Digilent, is a USB oscilloscope. So this cable here actually plugs right into your laptop, and you'll be able to capture these images directly on your laptop. These wires coming out here allow us to measure analog signals here with these first couple pins. Allows us to measure digital signals, and we also have in the middle here a signal generator that we could generate a audio waveform. And we'll be using that a little bit later on in the sequence of the labs. So all this is connected into this USB system. The first thing we need to take a look at is essentially what is the circuit that we're going to try and measure. So what I'm showing here are essentially the output LED that's going to be illuminated and the input switch that we want to measure. And what we want to do is measure how long the time is between when this switch closes and when this LED turns on. We can think about this switch as being connected to an input pin, and we can then think about up top here essentially being the microprocessor actually doing the processing. So this input pin goes through the microprocessor, driving this output pin. Now what that means is, if I would like to figure out these times, what I can do is attach my oscilloscope to here and here, like so, and I'll be able to see when does this signal on this pin, this input pin here, go from VDD, which is our high voltage or our logic high, to being essentially a logic low when that is grounded by the switch closing. I'm going to also connect another channel over here on these other two pins, like so, and now I'll be able to see when the actual LED turns on based on this going here from a logic 0 to a logic 1. Here is our analog discovery board all set up and plugged into my laptop via USB cable. And what I want to do now is essentially connect it up to the system. Now I have here channel 1, which are these two origin leads. What I'm going to do is I'm going to connect these up so that they are on the switch. Now one of these lines that I have here you can see is orange with a white line on it. That's going to be our negative voltage, essentially our ground voltage. So what I want to do is connect that to a point that is grounded. Now the ground connections are these top two connections on the Beaglebone, as we've talked about in class. So I'm going to slide this in right like so. My other connection, which is does not have the white line, this is the positive connection. What I want to do is connect this up to the switch. Now my switch is connected. If I look here, here is my pull-up resistor right to this row right here. So here's the resistor. This is the high voltage going through here. This line here then runs over to the switch. So if I put it right into that row right there, I'll be able to see the switch. Now the next two lines I'm going to connect up are the blue lines here. So I want to connect again this blue line with the white wire on it to a ground connection, which I actually have left over here, this white wire kind of hanging here. I'm going to plug in like so, because I don't have another one of these adapter pins. And I'm going to take the other side of it here, and I want to plug this into actually where the LED is that's turned on, which that happens to be right here. Now what will happen is, as the lights are turned on and off, we can actually see things happening in the program. So with that being set up now, what I'm going to do is plug in my analog, or plug in my board here. Like so. Let the board boot up, and I will connect to it, and we'll actually see the LED blinking on and off. So here I have my program running, and we can see that this LED is blinking on and off, essentially blinking once per second on and off, as the program that I passed into it does. We can also see how we can change and have a program where the push button controls the LED as it's doing right now. So at this point, I've started the Analog Discovery Digilent Waveform software, and I have this window that's showing in front of me right now. What I'm going to do is I'm going to start my LED toggling, so we can see that on the screen now where it is blinking at a 500 millisecond rate, so on and off once per second. And what I want to do is I want to start my oscilloscope up. So the oscilloscope is opening, and we'll see it momentarily here as it comes online. So it is here, and my LED is connected to channel 2. So I'm going to turn off channel 1, and I'm going to start the oscilloscope running. Now we see right here, don't really want my tooltips on, we see that this is going on and off, and I can adjust this, slide it back and forth a little bit, but we can see that the distance here to here is pretty constant. That's good. That's what we'd like to see. If I stop acquisition here, what I can do is slide back and forth, and we can see that this is pretty darn close to 500 milliseconds, which is what we would expect it to be. I can also take and turn a measurement on here. So what I can do is measure the horizontal, the period. Whoops, and I want it on channel 2. So we can see that my period is 1.00098. So it's a little bit slower than once per second, but not that much. My frequency, can also measure that. And we can see that it is essentially 999.02 millihertz. So pretty darn close to 1 hertz. So we've got this basic measurement ability. Now what I'd like to do is change the focus of what I'm doing. So I want to essentially measure the time latency. So what I'm going to do is I'm going to change programs to begin with. So let's stop this program that is blinking the LED, and I'm going to switch to my push button program. So now we see that pushing the button changes the light. Now what I'd like to do is also do that with my program here. So I'm going to start this running, and we can see that when I press the button, they go up and down. Now what I'd like to do is figure out what is the time difference between these two. So to do that, what I'm going to do is start to zoom in on the time a little bit. So I need something that is a little bit higher resolution, possibly like 10 milliseconds per division, so we can see it moving up and down. But I think I'm going to start with a larger time like so. And what I want to do is get one that's good here. And I wanted to stop there, but I didn't stop. So okay, I've stopped the signal. Now what I'm going to do is essentially zoom in on this. So I want to switch to 10 milliseconds per division. 1 millisecond per division. Here I'm going to have to probably scroll a little bit over so that my, whoops, I went too far. So let's go back up to 10 milliseconds per division. But we can see that there is a little bit of a lag between this, which is my push button going down, and this is my LED changing. If I switch this to 5 milliseconds per division, we can see that time difference there. 2 milliseconds per division. And now if I start adjusting, whoops, I want this back to what I had before. So that I can actually see the transition. And I can zoom in very nicely on this, 1 millisecond. So this distance between here and here is 1 millisecond. And I can adjust ever so carefully. So I can see right there, you notice the signal goes up and then starts down. That's where things start on the push button. And then here's where it starts on the LED, that same change going on. So we have essentially the distance between here and here, which is almost 1 millisecond of latency. If I zoom this in a little bit farther, so there I'm at 500 milliseconds. I can adjust this and we can see the same thing going on here. And if I drag this more towards the center, now when I zoom this in, we can really see that essentially right here is where the push button started to get pushed, and then 200, 400, 600, 800, just shy of 1,000 microseconds later, the LED starts turning on. So that is the latency between when the push button is pressed and when the LED starts responding. I can get better granularity by using the cursor capability. So if I take any of these spots that are marked with an X, right here for example, I can see the time value, 459.752 is right where I'm at there. If I go then down to here where we start seeing the change on the LED, 458.746, we can do the math between those two, and we can see that we've got 1.006 milliseconds distance or latency between when the push button is actually pressed, which is this upper line, and when the LED starts to change. Now other things we can adjust here, I can move these signals up and down by changing the voltage. So you see how I'm moving the LED signal up by dragging it, and I'm dragging this other signal down. This 0 volts here, this is an indication that this is a logic low. This 3 volts up here is a logic high. Same thing here. Now cursor 2, you'll notice the range is a little different. I talked about these horizontal distances here being time measurements. The vertical distances are voltage measurements. So channel 1, which is this channel down here, is set to 1 volt per division. So this is 1, 2, 3 volts going up here. This other one is set at 4 volts per division. I can change that. I can make this also be 1 volt per division. Now when I drag this guy down here, we can see that they essentially look about the same. So they're both going from essentially 3.3 volts, which is what this is showing, 3.2 volts, down to essentially ground. So we're down in the millivolt range. So we can measure time across the horizontal and voltage across the vertical axis. Voltage is analog. We need to do the translation to realize that anything that is around 3 volts is a logic high. Anything around 0 volts is a logic low. At this point in time, you should be able to understand how you go about connecting the Digilent Analog Discovery board up and using its oscilloscope functions to measure both frequency and time durations of analog signals. You should be able to measure the difference in time between two signals using the resolution on the display, and you should be able to understand the analog voltages that each signal has based on looking at or reading the display from the analog discovery device. That brings this video to a close.